Hello, can you hear me? Hello, can you guys hear me? Like, hear my voice? Am I audible? Please, just give a response in the chat. Hello, here, Ashlesh, Harsh, Sharma. Hello. Background noise is there. Wait. Is the background noise still there? Can you guys tell me if the background noise is still there? Background noise. Okay. Wait 1 minute. How about now, guys? Uh, is it gone? Is my voice clear? Okay, so now I'm gonna begin. Hello, guys. Uh, my name is Ayandeep Sengupta. Today, in this session, we're gonna talk about immunology, like how our body responses to any infection we might have, like any pathogens, any non-self bodies that enter our health system, or like anything that's a pathogen that enters, let's for example uh, blood flow, or like under the skin, your lungs, your heart, your brain for instance. These things, if they enter our system, they can like risk our health. So in these cases, if in everyday life we need our immune system. Our immune system is like one of the most important systems in our body. You guys know, right? About other systems like endocrine system, for example, and like excretory system and all. Immune system is one of the most important ones. So yeah, what should I say? Good evening, everyone. And so yeah, here let's start. So today's session is called Immunology. Yeah, our body's defense story, and I choose that word story on purpose because that is really what it is. It has like characters, it has heroes that arrive in minutes, and like specialists that take days to train. It has so many, what do you call it, like disguises, false alarms, narrow escapes, and memory system so good that it can recognize any enemy it met years ago, and in a matter of time. By the end of today, I promise you this: you will never look at like pepper cut or a fever or a vaccine in the same way again. So let's move to the next slide. These are our topics today. We'll start with an introduction, why immunology matters at all, and what we're actually defending against. Then we'll meet the pathogen themselves, for example bacteria, viruses, fungi, parasites, and how your body tells the difference between you and not you, like self and non-self. That is one of the most important things here. From there we will walk through your physical and chemical barriers, the walls and the coats of this whole system. Then we get into immune response itself, and here's it's where it gets interesting, because your body actually runs two different strategies at once. First is the innate immune response, which is fast, generic, and always ready. The second is adaptive immunity, slower to start but incredibly precise. And it's the reason you don't catch particular disease like chicken pox, for example, or let's say COVID in some cases. It's not always, but COVID, or let's say diseases like typhoid. These diseases don't happen twice. If the strain is different, it can happen again, but in general cases it doesn't happen twice. If you have chicken pox once, you will most probably be free of it for the rest of your life. After that, we'll look at the complement system, a backup army of proteins. Most people have, like, you guys might never have heard of it. We'll map out the full immune response timeline, compare the natural immunity to vaccines, and talk about passive immunity, including how a mother protects her baby before it's even born. Then we'll turn to the cutting edge immunotherapy and cancer, where scientists are now reprogramming the immune system itself to hunt tumors. We'll close with where this field is heading next, and the summary to lock in everything we've covered. So let's start. Let's see what the comment says for once. Yeah. Let's start with a question. I want you to actually sit with for a second. Ask yourself, what does it take physically to keep you alive today? Not for the next 50 years, today itself. You can see this picture. Take a look at this for a moment. What you're looking at is essentially the cast of characters we're going to meet over the next 90 minutes. The barriers, the cells, the chemical signals, all working together as one coordinated system. I'm not going to explain every piece of this right now, because we're going to build up it piece by piece, slide by slide, until this picture makes complete sense to you. But I want to keep this image in the back of your mind as a kind of anchor. Every new idea we cover today is really just one more layer being added to the same picture. Let's start adding those layers. Why immunology matters? So why does it matter? Let's talk about these 4 reasons, and I think by the end of these 4 points, you will have a completely different appreciation for what your body is doing right now in this room, while you're just sitting there and listening to me. First, everyday protection. Your defense is layered. Think of your body less like a single wall, more like a castle with multiple rings of defense. Physical barriers, your skin, your mucus, your stomach acid, these things stop most of the germs before even they get inside. But nothing is perfect. So behind this first wall, you have fast responding cells that can contain a threat almost immediately, buying time for the most specialized targeted defenses that are built up in the background. That's the layered part. Speed and precision working together, not instead one at a time. Second one is layered defense system. This is happening every single day, whether you notice it or not. Your immune system is constantly blocking microbes before they ever cause a symptom you'd recognize as an illness. You don't feel your body winning most of these battles. You only notice it on the rare occasions when it loses one, almost loses one. and the infection actually takes hold and starts damaging the tissues or cells, or maybe draining the fluid of your body, etc. In other words, most of your immune system's greatest victories are like invisible to you, can't even feel them at all. Uh, and the third one is like one of my favorite ideas in this whole field: speed now and memory later. You, your early responses act within hours to slow down an infection's growth, that the speed now part, but your immune system also builds memory so that you're ever exposed to that same threat ever again, your response is dramatically faster. Okay, like if you get, for instance, I said chicken pox. If you get like the virus comes again to attack your immune system or your body, it will like eradicate the virus so fast that you won't even have the disease. So, and fourth, why immunology matters in medicine. Vaccines exist because we can train the memory of our immune system deliberately, safely, and without you ever having to like getting seriously ill. Like it was not that case all the time. Sometimes we get some mild fever or rashes or permanent marks or scars around the body where we take the vaccines. These things can happen, but mostly it is very very safe, and it gives you like it takes you out of the danger from the disease. So, understanding the inflammation process explains why you get symptoms like redness and swelling, and why chronic long-term inflammation can actually be harmful. And in one of the most exciting frontiers in modern medicine, new cancer therapies are learning to boost or even redirect immune cells so that they attack the tumor cells directly. We're going to spend real time on that at the end of today's session, at the end of part. And genuinely, one of the most remarkable stories in modern science is that we can like change how immune cells divide, they respond, and according to that we can improve our immune response. That will make us able to even get out of like say a cancerous tumor. We can like treat it without even the operation, we like the surgery we need to do in everyday like the patients do surgeries for cancers in, suppose, in some organ in your stomach, the like organs like stomach or the say placenta or something. If cancers are there, we need to, most of the time we need to surgically remove them. Sometimes the cancer grows in some places. It's like very difficult to remove the cancer cells because they have invaded like vital spaces of our body, like say spine or brain or lungs. When we try to remove that tumor part, it it can cause damages around the body. Like if it causes some damage in some part of the brain, it can take the ability from you to talk. Like you will not be able to walk properly. You will some part of your brain will be damaged so much that you will like have so many side effects of that surgery. So we can redirect our immune cells in such a manner that they can ruin, like they can uh, ruin the tumors, they can eradicate the cancer by themselves only without needing any more surgery. So let's go to the next slide. Of its own to reproduce. To make copies of itself, it has to break into one of your cells and hijack that cell's own machinery, essentially turning your own cell into a virus factory. The flu virus, for example, the COVID-19, both work exactly this way. This is a big part of where like why the viral infections are so tricky to treat. The enemy is hiding inside your own cell in these cases, because they don't have you might have heard of the processes like translation, transcription, and DNA replication. These viruses, without a host cell, they cannot do any of these things. What they do is they have reverse transcriptase, like they have reverse transcriptase. So what they do is they inject their DNA or their RNA into the host cell. They make the cell make the proteins that the virus wants for themselves. Like they trick the machinery of the cell so that the translation process is like making protein from the RNA code. So that machinery, if the virus gives its own RNA to the cell will like create the protein according to the code that the virus has in its own RNA. So the translation process will be taken over by the cell, and the cell itself will produce the harmful proteins that will help the viruses to spread the toxin or divide itself, like to get the resources to divide itself to reproduce. And third one is fungi and parasites. Fungi are more complex than bacteria. They're built more like your own cells, and some cause infections you've probably heard of, like athlete's foot. That happen because they often go around fields without wearing shoes, and also they the fungi and parasites, they attach to their cell, attach to their legs, feet. So these are the very different kinds of enemies. With these three very different strains of pathogen, we need different strategies. And this raises the next question, that how does your own body even know that one of these has shown up? Like which one of these has shown up? Yes, let's see if anybody has said anything. So yeah, antigens, the immune fingerprints. There are things called like you have heard of antibodies, right? Antibody and antigen reaction and all. So antigen is a kind of you can say protein. Antigen is a kind of special protein that gives one pathogen a unique representation. Okay, so every other organism has a different antigen. The antigens, the protein themselves will have different structures that we can uh, differentiate them by. Okay, every, as I said, every microbe, they carry surface molecules like surface proteins they have, and these molecules essentially stand out to your immune system as like it's not your own body's something, it is not you, it's non-self. Different pathogens display different antigen patterns. Think of them as like unique ID badges. No two invaders look exactly the same. And here's your body, here's how your body like actually uses this information. Immune cells read these antigens in order to aim the right defenses at the right target. This is really important design principle, because without it, your immune system would just be attacking randomly, wasting energy on harmless cells while missing the actual threat. Antigen recognition is what turns a chaotic response into targeted one, and this is why recognition has to come first before anything else can happen. Accurate identification is what starts our target response instead of a random attack. Later in today's session, when we talk about antibodies and T cells, you will see that they are the core antigen matching machines. They hunt by comparing what they encounter against and antigen patterns they have learned to recognize. Everything downstream in this story depends on getting these things on the first step right. So now we understand the enemy. Now we understand how your body identifies it. The next question is, what stops these invaders before they even reach your cells in the first place? Physical and chemical barriers. This is your first line of defense, and honestly, it's the layer most people never think about, because when it's working, absolutely nothing happens. Let's start with the most obvious barrier, your skin. Skin forms a tough waterproof shield that prevents the vast majority of microbes from ever getting in. And here's a detail I love. Your skin is constantly shedding cells. And that constant shedding usually helps remove the germs that have managed to hitch a ride on the surface before they can settle and establish themselves. Your skin, in a very real sense, is self-cleaning. But obviously, not every surface of your body can be covered in tough, dry skin. You need to breathe, eat, and digest. So, your body uses a different strategy in those areas: trapping and chemically killing. Mucus lining your airways and gut physically traps your particles so that they can't reach the cells underneath. Then tiny hair-like structures called cilia sweep those trapped microbes upward and out, where they are either swallowed or expelled entirely. And in your stomach, acid at a pH of roughly say 1 to 2, which is extraordinarily acidic, destroys many of the bacteria you ingest with food and water before they ever get a chance to cause trouble. And finally, there's a barrier most people don't even think of as a barrier: your microbiome. The friendly, harmless microbes that already live on and in you take up physical space and consume available nutrients, effectively crowding the crowding out the invaders before they can gain a foothold. In a strange way, some of your best defenders aren't the immune system at all. They are other microbes occupying territory or so hostile ones can't even move in. So self-cleaning I talked about, microbiome I talked about. So tears. Tears are a form of chemical defense. Tears contain an enzyme called lysozyme which helps break down the bacterial cell walls. That's a big part of why your eyes are able to resist everyday exposure to the environment without constantly getting infected. So next is innate immune response. The moment something breaches your barriers, your body needs to do three things almost instantly: spot the intruder, sound the alarm, and open the gates for the reinforcements. Spotting the intruder happens through built-in sensors called PRRs, pattern recognition receptors, PRRs. These sensors don't need to learn what a threat looks like. They're already built to recognize common patterns that show up across huge numbers of different microbiomes. The moment they detect one of these patterns, local tissue instantly flips from normal to under attack. Next comes sending alert. Infected cells release chemical messengers called cytokines, which are essentially distress signals. These signals guide nearby immune cells directly towards the exact spot of the infection. Think of it as a very precise chemical, like come here, we need help, like a flag or something. And finally, opening the gates. Blood vessels near the site of the infection widens, which increases blood flow and helps delivering the defenders more quickly. At the same time, the walls of those vessels actually loosen up, so immune cells can squeeze out of the bloodstream and into the infected tissue itself. This is the beginning of what you'll come to recognize later in this section as inflammation. So detect, alert, and open the gates. Now let's meet the first cells to actually show up and fight. Neutrophils. Rapid attack mode. My phone is getting a little bit hot. Let's wait a minute. Can you guys hear me? Like my network went off for a minute. If you can hear me, just say one hi or something here. Okay, thanks. Let's continue. Sorry for the disruption. Meet the neutrophil. Your body's first responder, and honestly, the most abandoned soldier in your entire like army of defenses. Neutrophils make up roughly 60 to 70% of all the circulating the WBCs, like white blood cells. That's an enormous proportion, and it tells you something important. Your body has built for sheer numbers and speed here. Neutrophils are built for speed. They can reach the site of an infection within minutes. So how do they actually fight? They engulf invading microbes in a process called phagocytosis, essentially swallowing the pathogen whole and digesting it from the inside. But that's not their only trick. They also release toxins, chemically and toxic chemicals directly onto the invaders. They can cast out something called NETs, and neutrophil uh, extracellular traps, that is, which physically ensnare the pathogens like a net. Why do they matter so much, especially early on? They their rapid high volume attack can slow an infection significantly before more specialized cells even arrive on the scene. But this comes at a cost. Many neutrophils die in the fight. And here's a detail that reframes something you've probably seen your whole life without understanding it. The pus you see around an infected cut or wound is largely made up of collected dead neutrophils. That's not a sign of something going wrong. That's the visible evidence of your body's first responders giving everything they have. Macrophages. Next, let's meet this macrophage. And if the neutrophil is your rapid response soldier, the macrophage is closer to a combination of cleanup crew and intelligence officer. First, they are a frontline cleanup crew. Macrophages engulfs germs, but they also engulf dead cells left behind from the fight, clearing the battlefield. This reduces, further tissue damage and help prevent the infection from spreading any further. Second, this is the part I find genuinely fascinating. They share evidence. After digesting a pathogen, macrophages display fragments of antigens on their own surface, essentially so that other immune cells, especially like T cells, can learn exactly what to target. And this one step is what helps launch a much more specific targeted response later on, which we'll get to in the adaptive immunity section. Third, they support repair after the fight is over. Macrophages help switch the body out of attack mode into a healing mode, supporting tissue repair so that the area can return to normal function. So notice something important here. Macrophages aren't just fighters, they are also messengers, bridging fast generic innate response we're covering right now with the precise targeted adaptive response we'll cover in a little later. Keep that bridge in mind. So it's going to matter. Keep in mind. Keep that. Inflammation signals. Let's talk about inflammation. Because I guarantee every single person in this room has experienced it. Probably without ever understanding what was actually happening. You've heard of classic signs like redness, pain, heat, and swelling. Let's break down what actually causes each of them, because none of them is actually accidental. Redness comes from the extra blood flow. Blood vessels widen, brings more immune cells to the site of injury or infection. That boosted circulation also delivers oxygen and repair materials the tissue needs to heal. Pain is a built-in warning system. It's uncomfortable on purpose. It encourages you to protect the area while it heals, not to use it, not to touch it. But there's a catch. If inflammation sticks around for too long, the same process that's supposed to protect you can actually start damaging the healthy tissue. This is the difference between helpful short-term inflammations and harmful and chronic inflammations. The heat and swelling comes from the increased access. Warmth can actually slow down some microbes directly, while also supporting faster cell activity in the area, and the vessels near the site becomes leaky on purpose, allowing fluids, proteins, and immune defenders to enter the tissue more freely than usual. So, the next time you see a red, warm, swollen, slightly painful area on your skin, I want you to recognize it for what it really is. Not a malfunction, but a precisely engineered 4-part emergency response happening in real time. Just give me a minute. Have to check. The last stop in the innate immune response, the dendritic cells. And I have saved these for last on purpose because dendritic cells are the bridge to everything we're talking about, we'll be talking about next. Think of dendritic cells as frontline scouts. They patrol your skin and mucosal surfaces, keep capturing microbes soon after their entry. Essentially collecting evidence before the bigger response even kicks in. Here is the clever part. They turn microbes into a message. Inside the dendritic cells, the invader gets broken down into antigen fragments, and those fragments are then displayed on the cell's surface like a clear, unmistakable ID tag, specifically prepared for T cells to read. And then they deliver that alert directly to where it needs to go. Dendritic cells physically travel from the infected tissue to the lymph nodes and the places where T cells gather and wait. This is the critical link between fast innate detection and precise adaptive activation. So hold on to that idea, because we're now walking directly through that breach. Everything we've covered so far, there are barriers, neutrophils, macrophages, inflammation, and dendritic cells. All these has been about buying time and gathering intelligence. Now we get to see what your body does with that intelligence. Adaptive immunity. If the innate response is your body's first generic emergency team, adaptive immunity is the specialist division, slower to mobilize but far more precise. And it's the reason your body can remember an enemy for years, sometimes for life. So let's compare these two systems directly, because understanding the contrast is the key to understanding the entire half of the immune system. Innate immunity is fast and broad. It reacts within hours using built-in sensors tuned to common microbial patterns. The PRRs we already talked about, it doesn't need to learn anything new. It's already there from day one. Its job is to buy time, slowing the spread of an infection and calling in more immune cells while something more precise gets built. Adaptive immunity is slow and precise. It takes days to get going at first because it has to actively select the right T cells and B cells out of the enormous pool of possibilities. Cells specifically suited to this exact threat, but once it's built, it targets one antigen at a time, making the response highly specific, almost like a custom designed weapon built for this one invader and this one invader only. So why do you need both? Because the innate defenses contain the threat, while adaptive forces scale up the background. And together these two systems create something innate immunity alone could never. Lasting protection through immune memory. That's the payoff we're building towards in this section. Let's just give me a minute. of my friends came. Sorry. Yes, you can see me. Yeah, let's start again. Yeah, T cells and B cells. Now let's meet two main players of adaptive immunity: T cells and B cells. These are both types of white blood cells called lymphocytes, and together they form the core of everything we're about to discuss. Let's start with B cells, the antibody makers. B cells mature in your bone marrow, and their specialty is producing antibodies. When a B cell gets activated, it transforms into something called a plasma cell, which then releases huge amounts of antibodies into your system and blood and tissues. Those antibodies work by tagging or blocking the invaders, essentially marking them so the other can finish the job. Now, the T cells, think of them as directors and destroyers. T cells mature in an organ called the thymus, and they either guide the overall response on or directly eliminate the threats. There are two major types which are worth knowing. Like helper T cells send out what I would like to call go signals. They organize and coordinate the entire immune response rather than fighting it directly. Killer T cells, on the other hand, remove infected body cells directly, stopping the infection from spreading any further. And here's why this partnership matters so much. T cells generally handle cells that are already infected, while B cells handle pathogens that are still free floating out in your blood and tissues, not yet inside a cell. Two different battlefields, two different specialists. Together they cover the entire range of what adaptive immunity needs to handle. We're going to zoom in on each of these cells: helper T cells, killer T cells, and B cells, one at a time, starting with the coordinators. Helper T cells. If adaptive immunity were on, let's say, orchestra, helper T cells would be then the conductor. They don't play the instrument themselves, but nothing happens correctly without them. What do they actually do? They act as coordinators, sending out signals rather than killing microbes directly themselves. Their real job is helping choose the right response for the specific antigen that's been detected. Why do they activate? Quite a lot, actually. Like who do they activate? It's like quite a lot of other different cells. They turn on the B cells, prompting them to become those antibody producing plasma cells we just talked about. They boost killer T cells, helping them find and destroy the infected body cells more effectively, and they even supercharge the macrophages, helping those engulf and clear invaders faster than they otherwise could. Now, here's why this matters clinically. I want you to really sit with this point. If helper T cells are lost, the entire defense becomes poorly coordinated, and even if every other piece of immune system is intact and functional, this is exactly why HIV targets. This is exactly what. HIV specifically attacks the helper T cells. Their numbers collapse. Both the antibody response and the T cell response collapse right along with them. This single fact explains why HIV is so devastating. It doesn't attack one weapon in your arsenal. It attacks the conductor standing in the front of the entire orchestra. Now we will go to killer T cell. Now let's meet the killer T cell, and true to the name, this is exactly where adaptive immunity gets direct. How do they find the target? Killer T cells scan the surface of the body cells looking for foreign antigens and which were being displayed there. If they find a match, that's a clear signal this cell is infected and it needs to be stopped immediately. Once they've locked on, they deliver the hit with precision. They form a tight contact zone with the infected cell, keeping the attack extremely localized and precise. Then they release two weapons, perforin, and which creates pores in the target cell's membrane, and gran enzymes, which enters those newly formed pores. And here's the outcome of those granzymes trigger apoptosis. Apoptosis means like cell death, essentially forcing the infected cell to self-destruct in a controlled way. Like destruction of the cell in a controlled way is called apoptosis. So this is what it triggers. Why this matters so much? Because it blocks the viruses from continuing to use your own cells as hidden factories to produce more copies of themselves. And the killer T cell isn't just killing an infected cell, it's shutting down a virus production line before it can do more damage. B cells becoming factories. Now back to the B cells, I want to show you just how dramatic the transformation really is. From the B cell to plasma cell, after activation, our cell changes into the B cell changes into a plasma cell, and the entire structure becomes built around one purpose, on one purpose only. It's like it is secreting the antibodies. This switch, and it's like the B cell is like say a gun, and here the antibodies are the bullets. Like the entire process is to just make this gun with this exact bullet, exact structured bullet, which are the antibodies. This switch essentially turns recognition into non-stop, dedicated production of one specific matching antibody type. And the output speed here is genuinely staggering. One single plasma cell can release approximately like 2000 antibodies per second into your body's fluids. Now multiply that by many plasma cells working simultaneously, and antibody levels across your entire body can rise extremely rapidly. What does this surge actually achieve? It dramatically increases the chance that an antibody will find and bind the right antigen quickly, purely through sheer volume and probability. The result is faster, more targeted protection arriving while the infection is still actively spreading, not after the fact. So now you have millions of antibodies circulating, each one matched to the exact invader you're fighting. But what to do with those antibodies once they find their target? That's our next story. The 3 antibody win moves. Neutralization, opsonization, and complement. The first is neutralization. Blocking the entry. Antibodies physically stick to the viruses or toxins, preventing them from binding to your cells in the first place. This stops the infection early, before the microbes ever gets a chance to multiply inside you. The second is opsonization. Tagging or for eating. Antibodies coat a pathogen, acting essentially like a bright, unmissable "eat me" label. This makes it much easier and faster for the macrophages to grab the coated target and clear it safely. The third is triggering complement. Punching holes, antibodies can activate something called the complement protein chain reaction, and which we're actually going to dedicate an entire section to shortly. Complement can directly damage a microbe surface and help finish the job that the antibody started. Block it, tag it, or trigger back up to destroy it. That's the antibody's playbook. Three different strategies, all achieving the same goal: stopping the invader before it can do more damage. The power of immune memory. Well, we have arrived at what I consider the single most important concept in this entire session: immune memory. This is the payoff for everything we have covered in adaptive immunity so far. Here is the headline fact. The second time it is much faster and much precise. On re-exposure to a pathogen you've encountered before, your immune response ramps up in just 1 to 3 days. Compare that to the days to weeks it took the first time around. That head start can genuinely stop the pathogen before you ever develop symptoms. How is this possible? What is this? Okay, sorry. How is this possible? Because memory cells stay on patrol. After an infection resolves, memory B cells and memory T cells remain in your body, ready to respond. Think of them as keeping a most wanted record of every antigen you've ever encountered. And when they do respond, antibodies surge to remarkable levels. Memory triggered responses produce somewhere between 100 and 1000 times more antibody than your original. First time response, that difference in scale is exactly why repeat infections with same pathogen are so often milder or prevented entirely. Speed now, memory later. Remember that phrase from earlier? This is what it was building towards. This is the entire biological basis of how vaccines work. That will come back to that directly later in the session. But first, let's meet a system that supports all of this from behind the scenes. The complement system. So let's take a break of 2 minutes. No, let's take a break of 3 minutes. We'll be coming back to the session at 4:06. Let's take a break for 3 minutes. See you guys in 3 minutes. So hello again. Let's start the session again. The complement system. This is probably the least famous part of your immune system, and yet it's involved in almost everything we've already talked about today. Let me introduce to the complement. Think of it as a backup army that always pre-positioned and that is always pre-positioned and ready to go. It's always on standby. Complement consists of roughly 30 different proteins circulating in your blood, sitting in an inactive off state because they're already pre-made. Your body doesn't need to wait to build them from scratch the way it does with antibodies. They're simply waiting to be switched on. How does it activate? Through a certain chain reaction. One activated one activated protein flips the next one, like a line of dominoes falling one after another. Each step in that chain amplifies the signal, which means the response scales up very quickly from a smaller to initial trigger. And speed is really the whole point here. Complement system helps control microbes early, often within minutes of entry, well before antibodies have even been produced. Think of it as a rapid fast responder support, arriving on the scene to back up your other immune cells almost immediately. Why it matters? Three reasons. First, it supercharges the other defenders. It helps antibodies and phagocytes clear microbes far more efficiently than they could alone. Think of it as a backup that makes every single hit from your other immune cells count for more. Second, it acts before antibodies even exist. Complement can tag and damage invaders within minutes of entry, which matters most during a first-time exposure, before your immune memory has had any chance to develop. And third, it bridges innate and adaptive immunity. One of its activation routes, the classical pathway, begins specifically when antibodies find to their target and recruit complements to help. In this way, complement links the raw speed of the innate immunity with the precision of antibody-driven adaptive immunity. It genuinely connects both halves of the story we've been building today. Three ways it starts. Complement can actually get switched on by three different ways, and I think this diversity is part of why it's so effective. The classical pathway is antibody triggered. When IgM or IgG antibodies stick to the germ and protein called C1 binds to that antibody, this route directly connects the complement to adaptive immunity. It's the pathway we just mentioned. The alternative pathway is surface triggered. Microbe surfaces can actually start this cascade without any antibodies involved at all. There's a low constant background activity, sometimes called tick over, that gives your body fast defense even on a first ever exposure, before any antibodies exist. And the lectin pathway is triggered by sugar patterns. Protein MBIL grabs onto unusual microbial sugar patterns your own cells simply don't have. Once it binds, and it flips the exact same cascade which switch as the classical pathway. Here's the elegant part. All of these three different starting points converge in the activating at the same central point, C3. These doors, one hallway, no matter how the alarm gets triggered, the actual response that follows is the same. Once the That shared pathway is activated, complement does three distinct jobs, and I want you to remember that as tag signal and what is this chroma? Tag it once that the shared pathway is activated, complement does three distinct jobs, and I want you to remember them as tag, signal, and destroy. First one is tagging. That's opsonization. The protein fragment called C3b sticks to the microbes, marking them as an easy target. Phagocytes can then grab C3b tagged microbes faster and swallow them sooner than the untagged ones. Signaling. That's inflammation. Fragments called C3a and C5a act essentially like a siren, pulling more immune cells into the area. They also help open up blood vessels, boosting the entry of the fluid and additional defender cells into the tissue. Last is destroying it. This is the dramatic finale. The membrane attack complex, or MAC, a group of protein C5b through C9, assembles directly onto the microbe's surface, forming an actual pore. That pore causes the cell to leak and ultimately burst, which is especially effective against many types of bacteria. The complement system's entire playbook is the tagging it, the signaling for backup, and then punch a hole straight through it to destroy it. This entire thing is executed in just a matter of minutes. When the control fails, when the control fails, what does then happen? In either of these directions, too little defense creates real vulnerability. Too little defense, it makes the immune system really vulnerable. Low complement levels can leave a person prone to diseases like gonorrhea. Because the bacteria of the disease gonorrhea is, you might have known, Neisseria gonorrhea. That bacteria is normally cleared through MAC pore forming step we just covered. Without functioning complement, that particular defense simply isn't available. On the flip side, your body also needs friendly fire prevention. Your own healthy cells use regulator proteins, CD55 and 59 among them, for protection. Without these regulators in place, complement can actually turn and damage the healthy tissue, blood cells, and mistaking your own body for an invader. And this has real disease consequences. Loss of proper complement control is tied to conditions like PNH and lupus. Interestingly, some modern drugs are now designed to intentionally block complement activity, specifically in situations where it's turned harmful rather than helpful, showing just how precisely this system needs to be balanced. Key takeaway. Here are the key takeaways. One big idea. So this is all of it. You can see this picture. This is the whole thing clustered into one image. This is the lectin classical and alternative pathway. Immune response, timeline, and types. Let's take everything we have covered so far and lay it out on a single clock. Let's walk through what happens minute by minute and day by day from the moment a pathogen enters your body. At 0 hours, a pathogen crosses your barriers, remember skin, mucus, and stomach acid, and begins multiplying right at the entry site. At 4 hours, the innate alarm sounds, your PRRs detect the danger, and cytokines call in your fast receptors, the neutrophils and macrophages we already met. By roughly around 24 hours, containment. Macrophages are clearing the debris, amplifying signaling throughout the area, and preparing antigen display, setting the stage for the adaptive response to begin. Between 5 and 14 days, the adaptive peak, T cells and B cells expand in number, and the antibodies surge to specifically target the invader. This is the slow but precise machinery we finally reaching the full strength. And at 14 plus days, memory cells remain in your body long after the infection has started, enabling a dramatically faster response if you ever encounter the same pathogen again. Let's talk about active versus passive immunity. Active immunity is the immunity you build yourself. Your own immune system produces its own antibodies, either after the natural exposure or after the vaccination. And critically, it also creates the memory B cells and T cells, setting you up for the faster responses in the future. The key trade-off here is a speed now versus lasting protection later. What is this guy's problem? Key trade-off is now of speed versus lasting protection later. Active immunity takes longer to develop, but the payoff is durable, long-term memory. Passive immunity is immunity you borrow. Instead of building your own antibodies, you receive ready-made antibodies from another source entirely. The upside is that protection starts immediately. Downside is that it fades because those borrowed antibodies gradually break down over time. And importantly, no memory cells are created in the process. Keep this distinction firmly in mind, because our next two sections are built entirely around it. First, we'll look at active immunity through natural infection and vaccination. Then we'll look at passive immunity, including one of the most beautiful examples in all of biology: how a mother protects her baby. This is like antibody. You can see this is the core structure of an antibody. Two heavy chains and two light chains attached together through disulfide bonds. Here in between it's white only, but actually there are disulfide bonds in there to hold it together. Okay, so yeah, let's start how natural immunity actually forms. After an infection, your immune system builds antibodies and memory cells, exactly as we described a moment ago. The memory can protect you faster if the same pathogen ever returns. But here's why it's risky. To gain that protection naturally, you must face the real disease first, including potentially severe symptoms or complications. And while you're sick, you can spread that same infection to the other people around you. The practical lesson here is simple but important. Strong protection through natural infection is absolutely possible, but the cost of getting there can be dangerously high. Prevention is a far safer path than learning the immunity through an uncontrolled infection. That brings us directly to why vaccines exists at all. Vaccines solve the exact problem we just described, and they do it in three specific ways. First, protection that lasts. Vaccines create immune memory, exactly the kind we discussed earlier, so your body responds faster the next time it encounters the real pathogen. The speed can stop symptoms before you'd ever even feel sick. Second, training without the illness. Vaccines expose your immune system to a safe practice target, so it learns to recognize a threat without even experiencing the full damage of a genuine infection. And third, why this changed public health entirely. Vaccination spreads protection across the whole communities by reducing the opportunity germs have to spread from person to person in the first place. In a very real sense, vaccines turned immunity from a risky individual learning by getting sick strategy into a coordinated population-wide system of prevention. Vaccine types. Not all vaccines work in the same way. Let's look at the three major categories. Live attenuated vaccines. Use a weakened version of the here we use a weakened version of the actual germ, one that can still train strong immunity but without causing the severe disease, because it is so closely mimicking the real infection. This type of vaccine often builds especially broad and robust protection. Inactivated and subunit vaccines take a different approach. Inactivated vaccines, we use a killed germ, one that simply cannot replicate at all inside you. Subunit vaccines go even more minimal, using only selected pieces of pathogen, often key proteins from its surface. The mRNA vaccines represent the newest major approach. These deliver mRNA instructions directly into your cells, and your own cells use those instructions to make one specific target protein. Your immune system learns to recognize that protein, and then the mRNA itself simply breaks down and disappears, weakened, killed, and partial or instructional. 4 different strategies, all aimed at the same goal: training your immune memory safely. mRNA vaccines. Because mRNA vaccines are relatively new and were central to the COVID-19 response, let's slow down and look at exactly how they work. What gets delivered? A short mRNA message enters your cells, carrying instructions for building exactly one protein. That protein piece is completely harmless on its own, but it looks enough like the actual invader that your immune system takes notice. What it does not do is just as important. No whole pathogen is ever used, so an mRNA vaccine cannot cause the actual infection it's protecting you against. So, the mRNA itself is temporary. It typically breaks down within about 48 hours. Does your immune system actually learn from it? Yeah. Your cells display that harmless proteins on their surface, allowing immune cells to recognize it as foreign. This amounts to a practice run, one that builds real memory cells, setting you up for genuinely faster protection if you ever encounter the real pathogen later. Now, active immunity is powerful, but it isn't always fast enough. Sometimes you need protection immediately. That's where the passive immunity comes in. Remember, passive immunity is borrowed immunity. Let's revisit what passive actually means in practice. You have received ready-made antibodies rather than manufacturing from your scratch, and because of that, protection begins really quickly. Your immune system essentially skips the entire training phase we spent the last section discussing. When is this actually used? Primarily in emergencies, when waiting days or weeks for your own immune system to respond, or for a vaccine to take the effect, would simply be like too late. Classic examples include rabies exposure and treatment support after the snake venom envenomation. But remember, the key trade-off from earlier, it fades over weeks to months as those borrowed antibodies gradually break down. The critically and no memory cells form in the process, which means any future protection would require an entirely new dose. Passive immunity buys you time, it doesn't build lasting defense. Mother to baby immunity. And now, one of my favorite examples in all of the immunology, or mother protects her babies entirely through passive immunity at two distinct stages. Protection before birth. During pregnancy, IgG antibodies actually cross the placenta directly into the baby. These antibodies offer the newborn early backup protection while its own mother is still maturing and developing. Protection after birth. Colostrum, that thick early breast milk produced right after delivery, delivers a concentrated dose of IgA antibodies into the newborn, and regular breast milk continues that IgA support afterwards, coating and protecting the baby's gut and airways directly. What does this all mean? This all temporary passive immunity precisely designed by evolution to buy the baby time. The time for its own immune system to develop and mature safely, protected by borrowed defenses in the meantime. It's a beautiful, elegant biological handoff from one immune system to another. Let's shift gears and look what happens when scientists deliberately engineer the immune system to do something it wouldn't normally do on its own. That is fighting cancer. Monoclonal antibodies. Let's start with monoclonal antibodies. Why do they matter so much? Because they focus on exactly one target, which allows them to act extraordinarily high precision. This lets medicine treat very specific biological pathways instead of broadly affecting the entire body the way many older drugs do. So what exactly are they? Monoclonal antibodies are identical, lab-made antibodies, all engineered to aim one single target. They are designed to recognize a single molecule, almost like a lock and key match built intentionally in a laboratory rather than by your own immune system. You have very likely to heard of real world examples already, even if you didn't know there were monoclonal antibodies. Humira is used to help manage arthritis by targeting one specific molecule involved in inflammation. Herceptin is used in breast cancer treatment, targeting a specific cancer-related marker found on the certain tumor cells. So think about what this represents. Scientists took the exact recognition system your body already uses, antibodies matching antigens, and learned to manufacture it on demand, aimed at whatever target they choose. The idea is the foundation for everything else in this section. This leads to a genuine paradigm shift in how we think about treating cancer, built around two core strategies. The first is restoring. This means removing the signals that the cancer cells use to silence T cells that are sitting right near the tumor, essentially turning your own T cells back on so they can do their job. The second strategy is redirect. This means actively re-aiming immune attacks towards specific cancer targets that they wouldn't necessarily recognize or attack on their own. What does this change? Immunology is genuinely shifting from a purely defensive posture to something closer to the immune engineering in modern medicine. These approaches can successfully fight cancers that resisted older and more traditional treatments entirely. This represents a new role for the immune system altogether. And cancer therapies now actively recruit immune cells and antibodies as treatment tools in their own right. The overarching goal is elegant and in its simplicity. Make the body recognize tumor cells as dangerous again, and the way it should have all along. How CAR-T works. Let's look at one of the most remarkable treatments in modern medicine, CAR-T cell therapy. Broken down into 4 steps. Step 1. Collecting your T cells. Doctors remove T cells directly from the patient's own blood through a controlled laboratory process. Step 2. Reprogramming the targeting. Those T cells are genetically edited so they can recognize specific markers found on the cancer cells, markers they wouldn't have naturally recognized as dangerous before. Step 3. Grow an army. These newly engineered T cells are then multiplied into the millions in lab setting before ever being given to the patient. Step 4. Infuse and attack. The cells are infused back into the patient's body, where they hunt down cancer cells far more precisely and far more strongly than the patient's original unmodified T cells ever could. Let's take a step back and appreciate what this actually is. Doctors are taking a patient's own immune cells, upgrading the targeting system in a lab, and sending them back in as a living, self-replicating drug. This isn't just treating cancer with chemicals anymore. It's treating cancer with an engineered personalized immune system. Unmasking the tumors. Our final immunotherapeutic topic, checkpoint inhibitors. And this one requires understanding a clever, somewhat unsettling trick that cancer cells never ever have evolved. How do the tumors hide in the first place? Some cancers flip on immune system brakes. A molecule called PD-1 is a well-known example, which causes nearby T cells to essentially stand down. This makes the tumor look far more like normal, harmless tissue to passing immune patrols, allowing it to hide in plain sight. So what do checkpoints drugs actually do? Checkpoint inhibitors block that fake stop signal from ever reaching the T cell. The goal is to restore the immune system's natural ability to recognize and attack the tumors, as it should have from the beginning. What changes afterwards? Once reactivated, the T cells target and destroy cancer cells far more effectively than before. I like to think of this as removing the safety lock once the tumor itself installed, so that the immune system can finally re-engage and do the job it was always capable of doing. So monoclonal antibodies, the restore and redirect shift, CAR T cell engineering, and checkpoint inhibitors, 4 completely different strategies, all built on the same underlying foundation we spent the first hour of today's session establishing. Now let's look ahead where this field is going next. Future directions. Next generation vaccines. Vaccine science itself is still advancing rapidly, and the 3 directions in particular stand out. The universal flu goal. Rather than targeting the parts of the flu virus that mutate every season, researchers are targeting the virus's stem regions, parts that change much more slowly over time. The aim is protection across many seasonal strains at once, rather than needing a brand new vaccine every single year. The pan-coronavirus approach follows similar logic, designing single vaccine that covers SARS, MERS, and COVID-like viruses together. By forcing the features those viruses tend to share, that would make the future variants far less disruptive than they have been so far. And personalized cancer vaccines take this idea even further. These use mRNA technology to train the patient's immunity specifically against the unique mutations found in their own individual tumor. The goal is tailored signal custom built for one patient that helps the body spot and attack their specific cancer. What happened? Microbiome and immunity. We opened today talking about the microbiome as a physical barrier. It turns out its role goes much deeper than that. What does your microbiome actually do for your own immune system? Gut microbiome helps calibrate your immune reactions, preventing your body from either over-responding or under-responding to threats. A balanced microbial community is matter for vaccines specifically. Differences in an individual's microbiome may actually affect how strongly certain vaccines protect them. A genuinely active area of ongoing research. And what happens when the balance breaks? A state called dysbiosis. Imbalances in the microbiome are linked to a higher risk of allergies and asthma, and the dysbiosis is also associated with some autoimmune conditions. Your gut, it turns out, it isn't just a barrier, it's an active partner in immune regulation. And finally, AI intelligence is now becoming a genuine collaborator in immunology research itself. Smarter cancer targeting. Machine learning can scan through entire tumor genomes to identify strong neoantigens, the unique markers a specific tumor carries. That directly helps the researchers pick better targets for personalized mRNA vaccine designs, the ones we just discussed. Faster protein insights. AI tools like AlphaFold can predict antigen shapes in a matter of seconds, a process that used to take researchers months or even years of laboratory work. This dramatically speeds up understanding of how immune cells might actually recognize a giant target. What does this change in practice? Discovery and design cycles are shrinking rapidly, making new therapies far more responsive to emerging threats. The overachieving goal is faster, more precise immunology, moving all the way from research lab to the patient's bedside faster than ever before. Let's bring this section together as one unifying idea. Prevention is becoming design. Vaccines train memory so that protection can stop diseases early, and the next generation of vaccine research is aiming for broader, long-lasting protection across many variants at once, not just one strain at a time. We're also seeing a genuinely new way to treat existing diseases, checkpoint inhibitors, remove cancers, stop signals, and reactivate T cells directly, while AI accelerates the discovery by predicting structures and identifying better immune targets faster than the traditional methods ever could. And the step back far